Welcome. Today we will have the second tutorial of the module of heat integration of the process. Okay. And topic for today's tutorial is development of heat exchanger network or pinch technology. So, let us see the first problem of today's tutorial. We have been given stream data that is now appearing on your screen. We have total of 4 hot streams and 3 cold streams plus 1 hot utility and cold utility. The supply and target temperatures T1 and T are also listed, like the first hot stream has the supply temperature of 720 degrees centigrade, target temperature of 320, the heat capacity flow rate is 0.045 megawatt per degree centigrade, and it has a heat transfer coefficient or also known as film coefficient of 2000 watt per meter square per degree centigrade. Similarly, H2 has supply temperature of 520, target temperature of 220, heat capacity flow rate of 0.04 megawatt per degree centigrade and heat transfer coefficient of 1500. And similarly, you can see the other temperatures. The hot utility has supply temperature of 1200 degrees centigrade. It is a high temperature process and the target temperature is 1000 degrees. The heat transfer coefficient is 3000 watt per meter square per degree centigrade, and the cold utility has supply temperature of 100 degrees and target temperature of 200 degrees, and its coefficient is 1000 watt per meter square per degree centigrade. For this stream data, we have to answer 3 questions. First is that for delta T mean equal to 20 degrees centigrade, we have to find the minimum hot utility and minimum cold utility as well as the pinch temperature using problem table cascade. Then the second question is development of the heat exchanger network for the process using maximum energy recovery principle or minimum number of heat exchanger unit, or what is known as the Tick-off heuristic that we have seen in the theory lectures. And we are also supposed to show the heat duty of each exchanger and the various intermediate temperature between units in the exchanger or in the network grid. And the third question that we have to answer is tabulation of the heat duty, log mean temperature difference, overall heat transfer coefficient and area for all exchangers in the network. Okay. So, we have to develop the data, process data for all the exchangers that we will design. We can make 2 assumptions in the solution. First is that there is no dirt factor or conductivity contribution to overall heat transfer coefficient, or we can say that overall heat transfer coefficient is given by 1 by U is equal to 1 by Hi plus 1 by Hu. Okay. Inside film coefficient plus outside film coefficient, the reciprocal of those. Okay. And then the second assumption that we are going to make is that the heat transfer coefficients or film coefficients of the streams do not change after splitting. That is, the split segment of any stream has same film coefficient as the original stream. So, with these 2 assumptions, we start our calculation. Now, we have seen 2 examples of problem table cascade in previous tutorial. So, I will go rather quickly over it. We have been given delta T mean equal to 20 degrees centigrade. So, we have to shift the temperatures of the streams by delta T mean by 2, that is 20 degrees centigrade. Okay. So, now I will directly show the problem table cascade. Okay. H1, the shifted temperature supply temperature T s star is 710 degrees centigrade, shifted target temperature is 3110, 10 degrees decreased, then H2 510 and 210, H3 590 and 310, H4 510 and 343. All temperatures decreased by factor of 10. Then the cold stream temperatures. Now, here we have to increase the temperature by 10 degrees centigrade. So, C1 supply temperature become 310, target temperatures become 910, C2 supply temperatures becomes 210, target temperatures becomes 560, and C3 supply temperature is 310 and target temperature is 570. And with this we now construct the problem table cascade as we did in earlier example. I will list all the shifted temperature intervals in the decreasing order, and then we shall show the stream population between these temperature intervals. The stream H1 goes from 710 to 310. It has a Cp of 0.045. Then H2 goes from 510 to 210. Then H3 goes from 590 to 310. Then H4 goes from 510 to 343. The Cp values I am listing now: H2 0.4, H3 0.04, not 0.4, H3 0.05, H4 0.02. Then similarly for C1, C2, C3, the cold streams, C1 goes from 310 to 910, with heat capacity flow rate of 0.043. C2 goes from 210 to 560 with heat capacity flow rate of 0.02, and C3 goes from 310 to 570 with Cp of 0.0667. And now we have to list the delta T interval, then summation Cpc minus summation Cph for that particular interval, summation of the heat capacity flow rates for cold stream minus summation of heat capacity flow rate for hot stream, then delta H interval, then we have to find whether the interval has surplus or deficit of heat, and finally the after hot utility addition, the surplus deficit. So now I will directly list the values. We have seen the calculations before, and then calculation of this detailed calculation of the problem table cascade I am leaving as an exercise for you. delta T interval 0, 200, 120, 20, 10, 50, 167, 33 and 100. Then summation CPC minus summation CPH 0.043 minus 0.002 minus 0.052 0.147 sorry 0.0147 then 0.0347 minus 0.0253 minus 0.0053 So, that is summation CPC, summation CPH, and then when we multiply delta T interval and that we get delta H interval. So, that values also I am going to write now 8.6 minus 0.24 minus 1.04 0.15 1.74 minus 4.23 minus 0.18 minus 2, and then we have to see surplus deficit, like in the first interval we have deficit. So, minus 8.6, then minus of minus 2.24, so minus 8.36 and so on and so forth. Again I am giving the direct values, I leave the calculation as an exercise. And then we see that the maximum negative or delta H or maximum deficit occurs in the interval of 560 to 510 as minus 9.21 megawatt, and we add that much of hot utility and then everything balances off. We get pinch at temperature of 510, where the total delta H becomes 0. Thus, after all summation we are left with 6.41 megawatt to be removed by cold utility. So, we have the answers with us now. QH min is equal to 9.21 megawatt and QC min is 6.41 megawatt. The pinch temperature, shifted temperature is 510. That means for hot streams the temperature is 510 plus 10, that is 520 degrees centigrade, and for cold streams the temperature is 510 minus 10, which is 500 degrees centigrade. So, these are the pinch temperatures. Now, with this information, so we have answered the first bit of the problem. that is development of problem table cascade and determination of QH mean and QC mean. Now, we go to the second bit of the problem, that is development of heat exchanger network using maximum energy recovery principle. Now, to do that, we first write the stream population. As we just determined, the pinch occurs at 520 degrees centigrade for hot streams and 500 degrees centigrade for cold stream. Then we list the Cp values here. H1 goes from 720 degrees to all the way 320 degrees. Then H2 has heat capacity of 0.04. H2 goes from 520 to 220. Then H3 goes from 600 to 320. With Cp value of 0.05. Then H4 again goes from 520 to 353. It has a heat capacity flow rate of 0.02. Then C1 goes from 300 degrees centigrade to 900. It has a Cp of 0.043. C2 goes from 200 to 550. It has a Cp value of 0.02, and C3 goes from 300 to 560 with Cp value of 0.0667. So, now we have at a glance the stream population and what are the streams and what temperatures they are going above and below the pinch. Now, we first consider the upstream region of pinch. Okay. So, there we shall start our problem. Upstream or above the pinch. Now, above pinch we have two hot streams H1, H3 and 3 cold streams. Okay. So, let us see what is the heat available with hot stream and what is the heat requirement of the cold streams. In addition, for above pinch region, we have some constraints as we have seen in the theory lecture. The constraints are Cph has to be lesser or equal to Cpc and number of hot streams have to be lesser or equal to number of cold streams. Okay. Now, let us see the heat surplus and heat requirement. H1 CP value of 0.045 and delta H is H1 is going from 720 to 520. So, 200 degrees difference. So, 0.045 into 200 is 9 megawatt. So, 9 megawatt are available with H1. Then similarly, H3, it has a heat capacity of 0.05 and above pinch region it goes from 600 to 520. So, a temperature difference of 80 degrees. So, 80 into 0.05 is 4 megawatt. So, 4 megawatts are available with H3. The heat requirement C1 has heat capacity of 0.043 and it is going from 300 to 500. So, 200 degrees jump and then the delta H that is required is 17.2. Oh sorry, we are considering above pinch region. So, C1 is going from 500 degrees to 900 degrees. So, 400 degrees jump, therefore, the delta H is 17.2 megawatt requirement, heat requirement of C1. Then C2 is going from 500 to 550, it has a CP value of 0.02. So, 0.02 into 50 is 1 megawatt and C3 has heat capacity flow rate of 0.0667 and it is going from 500 to 560 degrees. So, 60 degrees jump and therefore, it has a delta H of 4 megawatt or heat requirement of 4 megawatt. Now, we have to start making matches. We have the constraint of CPH lesser than CPC. Okay. Now, H1 can match, H1 has a CP value of 0.045 and it cannot match with C1 and C3, but with or C1 and C2, but with C3. However, the heat that is available with H1 is much higher than the heat requirement for C3, and therefore, what we do is that we split H1 and couple the segments with C1 and C2. Okay. Now, we take branch of or split segment of H1 with CP value of 0.005 and the total heat content of 1 megawatt, and then we couple this segment with C2. Now, this coupling satisfies the heat requirement of C2 and it is ticked off. So, now we start developing the heat exchanger network. Above pinch, 520 degrees hot stream temperature, 500 degrees cold stream temperature. Cp values I am listing here separately. H1 stream, we just thought of splitting it in Cp of 0.005 and Cp of 0.04, and then we are going to couple it with C1, the smaller segment. But before that, I will draw for other streams as well, so that later on we can start just putting the matches. So, we just made the first match of coupling the smaller branch of H1 with that of C2. And we write here the heat load on this exchanger 1 megawatt. Okay. Now, the next we couple the sub branch of H1 with heat capacity flow rate of 0.01 to C1. Now, C1 has quite high heat load, as we have already seen. It requires 7.2 megawatts. So, partially it is satisfied through the bigger branch of H1. Okay. So, that point we note. We couple the bigger branch of H1 with Cp of 0.04 megawatt per degree centigrade with C1. Heat available with segment of H1 is 8 megawatt, and it partially satisfies the heat requirement of C1 with 17.2 minus 8, that is 9.2 megawatt left out. So, now we make the second match. Segment of H1, the bigger segment, is matched with C1 and match with C1, and the heat load here is 8 megawatt. So, the segment of H1 is now ticked off. Okay. C1 is already ticked off. So, now H1 is completely ticked off. Okay. Now, we are left with one hot stream and one cold stream. However, the C1 stream is not fully satisfied. Okay. So, what we do now is we determine the temperature of the stream that is emerging from this 8 megawatt exchanger. exit temperature of C1 from heat exchanger of 8 megawatt. So, we write a simple equation, 8 is equal to 0.043 the heat capacity flow rate, T minus 500, and then determine T to be 686 degrees centigrade. So, this is essentially Q is equal to mCp into dt kind of relation. Okay. And then we determine the intermediate temperature of stream C1 as 686 degrees centigrade, and we write it here 686 degrees centigrade. Okay. Now, we are left with one hot stream H3 and second hot stream C3, second cold stream C3. Okay. Now, if you look at the heat capacity and the requirement, H3 has a heat capacity of 0.05, which is lesser than 0.0667. So, it can be easily coupled, and the heat that is available with H3 is exactly the requirement of C3. Therefore, H3 C3 can be coupled. So, that point we note. Heat available with H3 is exactly same as the heat requirement of C3, that is 4 megawatt. Moreover, Cph less than or equal to Cpc constraint is also satisfied, and thus H3 can be coupled with C3, and that ticks off both the streams as the heat requirement or the heat duty is satisfied. Heat duty on both streams is satisfied with 4 megawatt exchanger. Now, the only thing that is left out is the remaining heat duty of C1. C1 is emerging at temperature of 686 degrees centigrade from 8 megawatt exchanger. It has to go to 900 degrees centigrade. The heat that is required is exactly the same as the hot utility that is required, 9.2 megawatt. Okay. C1 requires to be heated from 686 degrees to 900 degrees with heat duty of 9.2 megawatt, and this is left out to be met with hot utility. So, we now place the last exchanger here, C1, the hot utility, and here the load is 9.2 megawatt. So, we have a total of 4 exchangers upstream 3 exchangers between process streams and one exchanger between hot utility and C1. So, that point we note. We thus have a total of 4 exchangers above pinch, 3 exchangers between process streams and one exchanger between hot utility and process stream. So, that completes the pinch design above or the pinch heat exchanger network design above pinch. Now, for below pinch region, we again draw a stream population diagram, and then we shall see what are the heat sources, what are the heat sinks. H1 goes from 520 to 320, H2 goes from 520 to 220, then H3 goes again from 520 to 320, H4 is also there. H4 goes from 520 to 353, C1 goes from 300 to 500, C2 goes from 200 to 500, and C3 goes from 300 to 500. I shall also list the Cp values and delta H, the heat available or surplus with each stream. H1 0.045, H2 0.04, H3 0.05, H4 0.02, C1 0.043, C2 0.02, C3 0.0667, and then the delta H megawatt, 9 megawatt available with H1, 12 megawatt available with H2, 10 megawatt available with H3, 3.34 megawatt available with H4, then 8.6 megawatt required for C1, 6 megawatt required for C2, and 13.34 megawatt required for C3. Okay. Now, the constraint that we need to satisfy is that Cph greater or equal to Cpc. Now, looking at the H values and the constraint, okay, we can see that we can match H1 with C1 without any trouble, because H1 has higher heat capacity than C1 and the heat available with H1 is 9 megawatt and that is required by C1 is just 8.6 megawatt. Okay. So, we can start matching. The first match we make is between H1 and C1. Now, since the heat that is available in H1 is more than that required by C1, the target temperature is not reached, but all the heat duty of C1 is satisfied. So, C1 is ticked off. Since the heat available in H1 is more than that in C1, the target temperature of H1 is not met, but C1 is ticked off as its heat duty is satisfied. And then, so now we make the first match of below pinch region between H1 and C1. And here we write the heat load, that is 8.6 megawatt. Now, the exit temperature of H1 from the exchanger can be again found out with simple formula. 8.6 is equal to 0.045 into 520 minus T, and T turns out to be 328.87, or we can approximate as 329 degrees centigrade, and that intermediate temperature we write here 329 degrees. Now, we are left with only 0.4 megawatt. On H1, and this can be met with cold utility. So, now we put the cold utility exchanger here 0.4 megawatt, and this ticks off the H1 stream because all of its heat duty is satisfied. Now, stream H1 stream H3 and H4 together have 13.34 megawatt of heat, which is sufficient to meet the heat requirement of C3. However, we are restricted by the Cp constraint. Okay. The Cp value of C3 is higher than both H3 and H4. We cannot directly couple. And therefore, we go for splitting of stream C3 in two branches. One branch with Cp of 0.05 and second branch with Cp of 0.0167. Okay. Then the branch with Cp equal to 0.05 is coupled to stream H3 and that with Cp equal to 0.0167 is coupled to H4. Now, with this coupling, the heat duty of both H3 and H4 is satisfied. So, those two streams are ticked off, and simultaneously the two branches of C3 are also ticked off. Okay. So, that point we note. With this coupling, both H3 and H4 are ticked off because their heat duty is satisfied, and both branches of C3 are also ticked off. So, we now show those two exchangers on the grid. The exchanger, we are going to split now C3. So, here we show the split of C3. Upper branch with Cp equal to 0.05. Now, this branch is coupled to H3 and the heat duty on this exchanger is 10 megawatt. The heat requirement of H3, and the second branch is coupled with H4 and the heat requirement here is 3.34 megawatt, which is the heat duty on H4. Okay. Now, we are left with now two streams, C2 and H2. Heat available in H2 is 12 megawatt and the heat demand of C2 is only 6 megawatt. And moreover, the Cp constraint is satisfied. You can see that the heat capacity of H2 is less than is higher than that of C2. Okay. So, now you can easily couple these two streams H2 C2. So, I am now placing an exchanger. The heat duty on this exchanger is the heat requirement of C2, that is 6 megawatt. And after emerging from this stream, the temperature of H2, exit temperature of H2 from heat exchanger is 6 megawatt transfer, 0.04 into 520 minus T. So, T turns out to be 370 degrees centigrade. So, that temperature we note here 370 degrees centigrade, and then we do not have any cold stream left. So, the remaining heat of H2 is then left out to be taken out by the cold utility, that is 6 megawatt. So, together we have 6 exchangers below pinch, four exchangers are between process streams, and 2 exchangers of utility. So, that completes our heat exchanger network design above and below pinch. Now, the third bit of the problem is that of determination of data, or let us say data tabulation for the exchangers. So, what we have to do now is just pick up the temperatures of the 2 streams in each exchanger above and below pinch, and then determine the LMTD, and thereafter determination of U, overall heat transfer coefficient, by the simple formula 1 by U is equal to 1 by HI plus 1 by HO. Okay. So, now I am giving the exchangers above pinch. We had 4 exchangers. So, let us call them HE1, the 4 megawatt is HE1, 1 megawatt HE2, 8 megawatt HE3, and 9.2 megawatt HE4. Now, this exercise is pretty straightforward, and I am giving you directly the data. You can calculate or you can tabulate the data. HE1, the entry temperature of hot stream, that we denote by TH1, 600 degrees, exit temperature TH2. So, here I write entry, exit for hot stream 520. Similarly, TC2 is entry for cold stream, that is 500, TC1 is exit for cold stream, that is 560, then delta TLM is 28.85, U is 600 watt per meter square per degree centigrade. You have to, how did I determine U? I took the film coefficients for the streams C3 and H3, like the streams which are coupled in HE1, and 1 by U is equal to 1 by HI plus 1 by HO, and the heat duty on HE1 was 4 megawatt, and then by the simple formula Q is equal to UA delta T, the area is determined as 231 meter square. Similarly, for HE2, I am directly giving the data. This is pretty easy exercise. I leave it to you for detailed calculation. Below here I give the formulae which I have just said. Formulae: delta TLM is equal to TH1 minus TC1 minus TH2 minus TC2 divided by ln Th1 minus Tc1 divided by Th2 minus Tc2 . This is one formula. The second formula is 1 by U is equal to 1 by Hi plus 1 by Ho, and the third formula is Q is equal to UA delta T Lm. So, using three formulae you can tabulate the data. I am directly giving the answers now. So, for 4 exchangers I am giving answers. For the exchangers below pinch I am leaving it as an exercise for you. Okay. So, that completes our tutorial on heat exchanger network synthesis using pinch technology, and this also completes the module on heat integration of the process. Thank you.